Welcome, deep divers. Have you ever paused to wonder how the incredibly complex machines that surround us, from life-saving medical devices monitoring the faintest electrical whispers of your heart, to the sophisticated audio processors in your headphones that make music sparkle, manage to extract crystal-clear information from what can often feel like a hurricane of noisy, chaotic data? It's often compared to finding a needle in a haystack, but with digital precision, it's more like finding the right kind of needle at the exact right moment amidst an infinite pile of identical-looking metal filings. Today, we're embarking on a deep dive into one of the truly unsung heroes of digital signal processing, finite impulse response filters, or FIR filters. Think of them not just as a cleanup crew, but maybe as the master sculptors of digital signals, meticulously shaping and refining data to reveal hidden truths.
And our guide for this journey, our navigational chart, if you will, comes from a foundational text in the field, Biomedical Digital Signal Processing by Willis J. Tompkins. This isn't just an academic textbook, it's really a practical blueprint. It expertly bridges the gap between intricate theoretical concepts and their real-world, life-changing applications, especially within the sensitive domain of medical instrumentation. It really helps you grasp the why this matters behind all the equations.
Our mission for this deep dive is to demystify FIR filters completely. We're going to pull back the curtain on what makes them so profoundly unique, why they've become absolutely indispensable in fields where accuracy is paramount, like, for instance, analyzing the tiny electrical events of an electrocardiogram or ECG. And then, crucially, we'll explore the fascinating how they're actually designed and implemented, taking them from concept to critical function. By the end, you won't just know what an FIR filter is, you'll hopefully have a genuine shortcut to understanding its power, armed with some surprising facts, and hopefully a few aha moments that stick with you long after our conversation.
Exactly. We aim to ensure you connect those intricate theoretical dots with their profound practical implications. Our goal is really to make these complex ideas intuitive, allowing you to truly understand the elegant solutions FIR filters offer in the face of noisy, complex data.
Right. So let's dive in. To truly appreciate the brilliance and, frankly, the necessity of FIR filters, we first need to understand the larger landscape they inhabit, the world of digital filtering itself. So let's unpack this. What's the fundamental, perhaps even, philosophical shift that happened when we moved from the old school, traditional analog filter to its modern, ubiquitous digital counterpart? What really spurred this massive transformation?
That's a great starting point. The distinction is, as you suggested, incredibly fundamental. Imagine analog filters as a craftsman working directly with the raw, continuous flow of the physical world. They operate on continuous waveforms. Think of the smooth, unbroken flow of a voltage signal coming directly from a sensor, maybe measuring temperature or sound or pressure. These filters are literally constructed from physical electronic components, resistors, capacitors, inductors, and operational amplifiers, all arranged in these intricate circuits. They react continuously to continuous changes. Digital filters, on the other hand, well, they live in a different domain entirely. They don't work with continuous waves, but with sequences of discrete numbers. These numbers are typically obtained by a two-step process. First, we sample that continuous analog waveform at precise, regular intervals, taking snapshots, if you will. Then we digitize each snapshot, converting its value into a precise numerical representation, basically, converting a wavy line into a series of distinct data points. Now, this widespread, almost universal adoption of digital filters in nearly every modern device today stems directly from the astonishing advancements in computing power. The easy availability and continuously increasing power of microprocessors and dedicated digital signal processors, well, they've revolutionized the game. This shift from physical analog hardware, which relies on the precise behavior of tangible components, to software algorithms or dedicated digital logic circuits, brings with it a whole cascade of significant advantages. First, consider their inherent immunity to noise. Analog circuits are notoriously susceptible to external electromagnetic interference. A stray electrical field, maybe a fluctuating power supply, or even a neighboring circuit can introduce unwanted noise directly into the continuous signal, altering its voltage level. Digital filters, however, operate on numbers. Once a signal has been sampled and digitized, its values are represented numerically. Noise introduced into the digital signal becomes more like a mathematical anomaly. It's often far easier to identify, isolate, and mitigate using clever algorithms. You're not trying to clean up a fluctuating voltage on a wire anymore. You're dealing with potentially corrupted data, which computers are exceptionally good at error correcting or filtering. It's like the difference between trying to clean a muddy river, which is analog, versus cleaning up a corrupted spreadsheet, which is digital. One is physical and messy, the other is numerical and logical.
That makes a lot of sense. So it's more predictable.
Exactly. And second, and this is critically important for reliability, is their precision and repeatability. The accuracy of a digital filter is primarily determined by the number of bits chosen to represent the variables, essentially, how many decimal places of precision you allow. This introduces a predictable, quantifiable round-off error. Contrast this with analog filters, which are plagued by the real-world imperfections of their components. Resistors change value with temperature, capacitors age and drift, and even small manufacturing tolerances mean no two identical analog filters behave exactly alike. Digital filters, conversely, maintain their exact predefined characteristics perfectly, irrespective of environmental changes or the passage of time. If you design a digital filter, it will behave identically in every device, every single time. This absolute repeatability isn't just a convenience, it's an absolute imperative in high-stakes applications like medical diagnostics or industrial control, where consistent, reliable performance is literally a matter of life or death or, costly failure.
Wow.
And finally, there's flexibility. This is perhaps the most revolutionary aspect. A single, well-written computer program can implement almost any kind of digital filter imaginable. This allows for incredibly easy modification, adaptation, and even dynamic adjustment of filtering characteristics without requiring any physical changes to the hardware. Imagine needing to update a medical device's filtering protocol to account for a new type of signal artifact. With an analog filter, that might mean recalling thousands of devices to swap out physical circuit boards. With a digital filter, it's often just a software update, perhaps even pushed wirelessly. This agility is a total game changer for innovation and maintenance.
So if you're working with something as incredibly sensitive and life-critical as, say, the tiny, often noisy electrical signals emanating from a human heart, signals that, if misinterpreted, could lead to a misdiagnosis or an inappropriate treatment, then this built-in reliability, unparalleled precision, and inherent adaptability aren't just desirable features. They're absolute paramount. It really is the difference between a consistent, trustworthy diagnosis and one that, alarmingly, might vary simply because the room temperature fluctuated or a component aged a tiny bit. That's a huge leap in capability and confidence.
Precisely. A huge leap.
Okay, so digital filters thrive on numbers. We get that. But how do they actually perform their magic? What are the absolute core, fundamental operations a computer or microprocessor needs to execute to take a raw stream of numbers and effectively filter a signal? It sounds like an incredibly complex task, but I have a hunch the underlying principles are surprisingly simple, maybe.
You're exactly right. The beauty of digital signal processing lies in its elegance and foundational simplicity. At its heart, any digital filter, no matter how complex its behavior or how sophisticated the task it performs, relies on just three fundamental operations. And these are precisely the operations that modern microprocessors are incredibly adept at performing, often at speeds measured in billions of operations per second. The first building block is storage for a fixed time interval, often conceptually represented as a delay block. Mathematically, this is denoted by the Z operator. If you see Z in a filter equation, just think delay by one sample period. Let's make this concrete. Imagine a digital assembly line. A number, x0, comes in. It doesn't immediately pass through. Instead, it enters a temporary holding cell for exactly one tick of our system's internal clock, one sampling period, t. During this time, the output of that cell is the number that was stored just before x0 arrived. At the next clock tick, x0 finally moves from the holding cell to the output, and a new number, xt, enters the input. This process continues. The output sequence is an exact replica of the input sequence, but every value is delayed by p seconds. A microcomputer achieves this by simply placing successive data points into designated memory locations, then recalling them at precisely synchronized clock times. It's how the filter remembers the immediate past, which is essential because filtering almost always involves comparing or combining the current input with previous inputs.
Okay, so memory is key. Delay. Got it. What else?
The second essential operation is multiplication by a constant. For each number in the incoming input sequence, the filter instantaneously computes the product of that number and a predefined fixed numerical constant, often called a coefficient. Ideally, this operation introduces no storage or time delay whatsoever. It's an immediate one-to-one mathematical scaling. Think of it as adjusting the volume or importance of a specific data point.
Right, like weighting certain past inputs more heavily than others.
Exactly. And the third, equally fundamental operation is the addition of two numbers. Similarly to multiplication, the filter instantaneously adds two numbers together. And again, ideally, this occurs without any storage or inherent time delay. These are the absolute basic arithmetic operations that every single processor is designed to do at its very core.
Store, multiply, add. That's it.
That's fundamentally it.
So to really boil it down for us, the designers and users of these systems, the fact that virtually all general-purpose microprocessors in existence today can perform these three incredibly simple fundamental tasks, store, multiply, and add, makes them astonishingly versatile and powerful for implementing any kind of digital filter. And here's the kicker, the crucial point for many applications. If these microprocessors are fast enough to complete all the necessary arithmetic operations to produce an output value before the very next input value arrives, then they can operate in real time. And for immediate monitoring, critical feedback, or control in applications like patient care, aerospace, or industrial automation, real-time processing isn't just a desirable feature, it's absolutely essential. It allows for instant responses to dynamic changes in the signal, which can literally be the difference between success and failure, or even, life and death.
That real-time capability is absolutely critical in so many fields. #TAG2, introducing finite impulse response, FIR filters.
We've now laid a really solid foundation, understanding the general principles of digital filters. Store, multiply, add. Real-time potential. With that stage set, let's zoom in on a specific and, as we'll soon discover, an extremely important type. Finite impulse response filters, universally known as FIR filters. What exactly makes them so distinct and gives them their special, often revered place in the vast world of signal processing?
Okay, FIR filters. They're precisely defined by a characteristic we call their impulse response. To grasp this, imagine a digital black box or filter. What if you feed into it a single, isolated momentary pulse? Think of it as a tiny, sharp spike of data. One sample with the significant value may be a value of 1, followed by an endless stream of zeros. This single spike is called an impulse.
Like hitting a drum once.
Exactly like that, a single hit. Now, an FIR filter's output in response to that solitary impulse will last for a finite duration. It will produce a series of output values, perhaps a few dozen, depending on the filter's design, and then after a certain fixed number of steps, the output will definitively settle back down to 0 and stay there. It doesn't continue indefinitely. This finite, predictable duration of its response to a single input spike is exactly why they're called finite impulse response filters. It's like throwing a pebble into a still pond and watching the ripples eventually die out completely, but in a very controlled, mathematically precise, finite way. This finite nature also leads to another crucial name for them, non-recursive filters. This means their current output depends only on the current input sample and a finite fixed number of past input samples. What's profoundly important about this is that they do not use feedback. There's no loop where past outputs are fed back into the calculation to influence the current output. This is a crucial distinguishing factor that sets them apart from their cousins, the IIR, or infinite impulse response filters, which by definition do use feedback. The implications of this no-feedback design, as we'll discuss, are enormous.
No feedback. That sounds important. Simpler, maybe.
In some ways, yes. Mathematically, we can describe the output ynt at any given time, nt, where n is the sample number and t is the sampling period, as simply a weighted sum of the current input xnt and a finite number of past input samples. So the equation looks like this: ynt bxnt plus bxnt plus bxnttt plus bnxntnt. Here, the BK values are what we call the filter coefficients. These coefficients are essentially the weights or importance applied to each input sample from the past. So B weights the current input, B weights the input from one sample period ago, and so on, up to Bn weighting the input from n samples ago. When we look at this in the z-domain, which is a powerful mathematical tool for analyzing discrete time systems, the filter's behavior is elegantly described by its transfer function, hz. For an FIR filter, he is always a straightforward polynomial in ZO. H plus B plus B0 plus B in ZO.
Okay, a polynomial. So this structure is more than just abstract math. It has real consequences.
Absolutely. This straightforward polynomial structure is absolutely key to understanding their fundamental properties and advantages. You can physically visualize this structure as a series of our delay blocks we talked about earlier, all arranged in a chain. Each delay block's output, a past input sample, feeds into a multiplier that applies one of those B coefficients. Then all these multiplied terms, the current input scaled, the input from one delay scaled, the input from two delays scaled, and so on, are finally summed together by a single adder to produce the final output. It's a very direct feed-forward process without any circular dependencies or feedback loops. This simple yet powerful architecture is at the root of FIR filters' unique and highly desirable characteristics.
Here's where it gets really interesting for anyone needing to actually use these filters. You've made a compelling case for the feed-forward structure. No feedback. Seems straightforward. My immediate thought is, if they're so inherently straightforward in those ways, why do other filter types even exist? What specific qualities elevate FIR filters to such a critical role in fields where precision is essential? Does this seeming perfection come with any hidden costs or complexities?
That's a perceptive question, and it really gets to the heart of the engineering trade-offs. While FIR filters do have some costs, as we'll see, their advantages are often so profound that they make them the undisputed champions for certain applications, especially where signal integrity is non-negotiable. FIR filters offer several truly compelling advantages that make them highly desirable, particularly in applications where any signal distortion is unacceptable or where absolute reliability is paramount. The first and arguably cornerstone advantage is inherent stability. This is not a characteristic you have to meticulously design for or painstakingly check. It's a fundamental property of every FIR filter. They are always stable. The reason for this mathematical certainty lies in their transfer function being a simple polynomial. In the z-plane, which is our analytical map for filter behavior, this polynomial structure means all their poles, these are mathematical points that dictate filter stability, are effectively located at the origin. Y0, 0. Think of the z-plane as a special analytical map for filter behavior, and the unit circle is the crucial boundary line on that map. According to the fundamental stability criterion for digital filters, a filter is stable if all its poles lie strictly inside the unit circle. Since the origin, Z0 is always comfortably inside this unit circle, FIR filters are, by their very nature, inherently stable. This is a huge deal.
So to put that in plain English, an FIR filter will never, ever run away on you. It won't suddenly start amplifying noise like crazy or produce wildly inaccurate readings because of some internal feedback loop going haywire.
Exactly. It just won't happen. In a medical instrument, for example, this inherent stability means the filter will always produce a predictable, bounded output. It will never generate uncontrolled oscillations or runaway signals, which is absolutely vital for patient safety, accurate data interpretation, and preventing catastrophic system failures. Imagine your heart monitor suddenly displaying meaningless runaway numbers. That's the nightmare scenario an unstable filter could create. FIR filters simply don't do that.
Okay, stability.
Yeah.
Check. That's huge. What else?
Second, and perhaps their most celebrated feature, is their capacity for precise linear phase response. This means FIR filters can be designed to have exactly linear phase characteristics. What does linear phase mean in practical terms, and why should you care? It means that all the different frequency components that make up an input signal are delayed by the exact same amount of time as they pass through the filter. This constant, uniform delay is incredibly important for maintaining the shape and timing of complex signals.
As a vivid scenario here, what's the profound implication if it weren't linear? Like, why does that uniform delay matter so much?
Let's go back to our medical example. Imagine a cardiologist in a busy emergency room looking at an ECG. They're trying to quickly assess if a patient is having a heart attack. They're specifically looking for incredibly subtle changes, like an almost imperceptible elevation or depression in the ST segment, this tiny part of the waveform just after the main QRS peak. Now, if your filter introduces a nonlinear phase response, it could subtly stretch or compress different frequency components of the ECG as they pass through. Different frequencies get delayed by different amounts. This means the ST segment, which is naturally very short and precisely timed, could get distorted. It might appear artificially elevated even when it's not, leading to a false alarm and unnecessary invasive treatment. Or worse, it might mask a real dangerous elevation, leading to a critical misdiagnosis. Linear phase filters are like a perfect transparent window. They might shift the entire view a little in time, but they never distort the objects within it. That unwavering fidelity in preserving crucial morphological shape and temporal timing information is why they are non-negotiable for critical diagnostic signals. IIR filters, for contrast, typically exhibit nonlinear phase, which can introduce those very undesirable and diagnostically problematic timing distortions.
Wow. Okay, so shape and timing are preserved. That's critical.
Absolutely. A third advantage is minimal finite length register effects. All digital filters, like any digital system, operate with finite precision, meaning a limited number of bits are used to represent numbers. This can lead to various errors such as quantization error, round-off noise, and even limit cycles, undesirable sustained oscillations that can top up, especially in recursive systems like IR filters. In FIR filters, because there's no feedback, any errors introduced at one point in the calculation are not fed back into the system to be re-amplified or propagated. They simply pass through and eventually die out with the finite impulse response. This non-recursive nature prevents the accumulation of errors, leading to much more predictable, robust, and reliable performance. With IRR filters, even tiny round-off errors can be fed back and build up, potentially causing significant, difficult-to-predict problems.
Less prone to internal digital noise issues then.
Much less prone and easier to analyze. Finally, there's the ease of design. Designing FIR filters to meet specific frequency and phase response specifications is generally more straightforward and less complex than for IR filters. Well-established, reliable techniques exist, such as the window method or frequency sampling method, that simplify the process. Moreover, many modern software packages automate the FIR design process, often allowing engineers to quickly compute filter realizations that are optimal in some defined sense, e.g. minimizing error in a certain frequency band, significantly simplifying the development cycle and accelerating the time it takes to bring new instruments to market. This design simplicity, combined with their inherent advantages, makes them a go-to choice for many engineers.
So if I'm understanding this correctly, an FIR filter is like the meticulously honest witness in a courtroom. What goes in comes out accurately just a little later. It offers a level of pristine signal integrity and predictability that, for certain applications, simply can't be compromised, even if it might sometimes require a bit more computational muscle. It seems like the cost is more about processing power rather than a compromise on the output quality itself.
Precisely. You've hit on the core trade-off. Their computational demands can sometimes be higher, especially for very sharp filters. But for many critical applications, that's a small price to pay for such profound advantages in stability and phase fidelity.
So we've got a solid grasp on what FIR filters are and why their inherent properties, like guaranteed stability and that pristine linear phase, are so incredibly valuable, especially in demanding applications like biomedical signal processing. But now the rubber meets the road. How do we actually make them work in a real-world system? How are these theoretical filters realized or built into a practical, functioning piece of hardware or software? Are we talking about dedicated chips or just lines of code?
That's an excellent question, as the how profoundly impacts the filter's performance and computational demands. And the answer is, well, both. They can be implemented in software on a general-purpose computer or microprocessor, or hardwired into specialized digital logic on a chip. There are three primary methods for realizing an FIR filter, each with its own computational considerations and trade-offs. The first and most common is direct convolution. This method directly implements the filter's difference equation, which we discussed earlier as that weighted sum of current and past inputs. For each new output value, the filter essentially takes its unit impulse response sequence, which, as we know, are simply the filter's coefficients, BAG, and slides it over a window of the present input and a finite number of past inputs. It's very intuitive. You multiply each sample in that window by a corresponding coefficient, then sum all those products to get one output point. If you have 30 coefficients for every new input sample, you're performing 30 multiplications and 29 additions.
Okay, that sounds like a lot of math, even for a modern computer, especially if the filter has many coefficients. What's the challenge here?
The challenge with direct convolution is exactly that. While it's conceptually straightforward and easy to program, it can become computationally inefficient, or just too slow, for higher-order filters. FIR filters tend to attenuate signals very gradually outside their passband. Engineers call this having slow roll-off characteristics. Imagine trying to block a specific frequency range, not with a sudden brick wall, but with a gentle sloping hill. To get a really steep cliff, a very sharp transition from passing frequencies to completely rejecting them, the order n of the FIR filter, meaning the number of coefficients, may need to be quite large. For instance, filters with lengths greater than, say, 30 or even 100 coefficients are common for achieving truly sharp transitions. This can demand significant processing power and memory, especially in real-time systems where you only have milliseconds between new input samples. It's like doing very long multiplication by hand for every single incoming number.
So for those really sharp filters, direct convolution might be too slow. What's the alternative?
For these higher-order FIR filters, the fast convolution realization method offers truly significant computational savings. This technique cleverly takes advantage of the fast Fourier transform, or FFT. Instead of performing direct convolution in the time domain, which can be slow for long sequences, the process moves into the frequency domain. Here's how it generally works. First, a block of input data, say 1024 samples, is converted to the frequency domain using the FFT. This gives you the frequency content of that block. Second, this result, which is now a spectrum of frequencies, is then simply multiplied by the frequency domain representation, also obtained via FFT, of the filter's unit impulse sequence. This multiplication is element by element and much, much faster than time domain convolution for large N. Finally, an inverse FFT is performed to convert the result back to the time domain, yielding the filtered output block.
Ah, the magic of the FFT. So we're doing some fancy math transformation to avoid other slower math, but the end result is faster overall.
Precisely. This entire process is then repeated for subsequent blocks of data, often using techniques like overlap add or overlap save to stitch the blocks together seamlessly and ensure continuous filtering. The underlying principle here is a powerful mathematical property. Time domain convolution is perfectly equivalent to frequency domain multiplication. Since FFT computations are computationally much less intensive for large data sets than direct convolution, especially as the filter length n increases, this method becomes highly advantageous for longer FIR filters. It's like sending all your mail in one big batch with an efficient courier service rather than individually addressing each letter and hand-delivering it. It can turn a task that might take n-log operations into one that takes roughly n-log n operations, a huge difference for large N.
Okay, direct convolution for simple filters, fast convolution for complex ones. Is there a third way?
Yes, there is. The third method for realizing FIR filters is an advanced recursive technique. Now, this might sound like a contradiction, given that we define FIR filters as non-recursive, meaning no feedback. However, this method uses a recursive structure involving something called a comb filter and a bank of parallel digital resonators. It's a specialized implementation that still results in an FIR filter's behavior overall, meaning its impulse response remains finite. It's particularly advantageous for frequency sampling designs, especially if a large number of the coefficients in the desired frequency response are zero. It can also be efficiently used for filters with integer-valued coefficients, which can lead to considerable computational efficiencies in specific hardware environments, especially with slower microprocessors or when very high sampling rates are required. It's about finding clever mathematical shortcuts to implement the same underlying FIR filter behavior.
It's truly fascinating how different computational strategies can be employed to achieve the exact same filtering goal. This allows engineers to optimize for sheer speed or memory efficiency, or even specialized hardware, depending on the filter's inherent complexity and the constraints of the system they're designing. It's always about picking the right tool for the job, tailored to the specific context.
Exactly. It's all about smart implementation.
Building on that, let's look at some concrete examples of FIR filters in action. This is where we see how these principles really come to life, showing how they can shape signals for incredibly specific purposes. From simply smoothing out bumps in noisy data to pinpointing subtle, critical changes in a complex waveform.
Indeed. Let's explore how FIR filters are specifically tailored for different signal processing tasks, leveraging their inherent advantages, especially that linear phase characteristic, to achieve remarkably precise results. First, consider polynomial smoothing filters. These filters are expertly designed to smooth out noisy signals by fitting a low-order polynomial, like a simple parabola or maybe just a straight line, to small successive groups of sampled data points. They effectively act as low-pass filters, brilliantly reducing high-frequency noise and eliminating jagged discontinuities in the signal. The mechanism is quite elegant. The filter determines the value of the polynomial at the center of each data group, replacing the original noisy data point with a much smoother estimated value derived from its neighbors. For example, for a 5-point parabolic smoothing filter, where L2, meaning it considers 2 points before and 2 points after the center for a total of 5 points, the difference equation is ynt minus 3xnt plus 12xntt plus 17xntt plus 12xnt3t, 3xnt4t.
Wait, I noticed the coefficients in that equation, 9 is 3, 12, 17, 12 minus 3. They're perfectly symmetric around the middle one, 17. Is that a coincidence or is there a reason for that?
That's a very keen observation, and it's no coincidence at all. That symmetry wasn't quite right in my first mention. The coefficients from the source are actually 3, 12, 17, 12, 3 for the 5-point smoother example, which are symmetric. My apologies. This symmetry around the central coefficient is a common and incredibly important characteristic of linear phase FIR filters. It's precisely this symmetry that guarantees their perfectly linear phase response. The order of the filter, related to L, or the number of points, can be chosen to achieve a desired roll-off. precisely controlling how much high-frequency content is smoothed out. Crucially, their phase responses are linear because of this symmetry, ensuring that this smoothing doesn't inadvertently distort the critical timing of the underlying signal, which is, as we've discussed, absolutely vital for medical data where every millisecond can matter for diagnosis.
Got it. Symmetry equals linear phase. Okay. What about other types?
Next, we have notch filters. These are highly specialized FIR filters designed to eliminate a very specific narrow band of unwanted frequencies. The classic example is getting rid of the ubiquitous 60 Hz, or 50 Hz in some regions, power line interference, which often contaminates biomedical signals. The goal is to kill that one frequency while passing all other frequencies with minimal attenuation. The design principle is elegantly simple and directly relates to our discussion of Hertz and the Z-plane. A highly effective way to design an FIR notch filter is to place zeros on the unit circle in the Z-plane at the exact frequency corresponding to the noise you want to remove.
Zeros on the unit circle. Can you give us a less technical analogy for that? Like, what does placing a zero do?
Certainly. Think of the unit circle as a kind of frequency dial in our mathematical Z-plane map. Placing a zero at a specific point on this dial is like creating a tiny black hole for that exact frequency. Any signal component at that precise frequency gets completely absorbed and attenuated down to nothing or very close to it. For example, if you have a sampling rate of 180 samples per second, placing a zero at an angle of 23 radians on the unit circle, which precisely corresponds to 60 Hz relative to that 180 Hz sampling rate, will effectively remove that specific 60 Hz line frequency noise. A simple notch filter, for instance, designed maybe to average out noise near a specific frequency, might look like YNT plus XNTT plus XNTTT. Depending on the sampling rate, this could act as a notch or a low pass. A true notch needs zeros on the circle. This capability is incredibly valuable for cleaning up biomedical signals like ECGs, which are very often heavily corrupted by this kind of power line hum, allowing for a much clearer visualization and analysis of the biological signal itself, which might otherwise be completely obscured.
Essential for getting a clean look at the actual heart signal then. Smoothing, notching, what else?
FIR filters can also be ingeniously designed to perform derivative algorithms, which means they approximate the mathematical derivative of a signal. Why would we want to do this? Because differentiation effectively highlights changes in slopes within the data, which are often key features in signals indicating rapid events. The simplest form is the two-point difference, YNT equals 1T XNTTTK. This filter effectively subtracts the previous sample from the current one and scales it by the sampling interval T. While it places a zero as ZEO1DC, which approximates the ideal derivative response for very slow changes, it also has a significant drawback. It greatly amplifies high-frequency noise. This is because its amplitude response does not go to zero at the highest frequencies, the Nyquist frequency. It lets through all the jitter. So it's often followed by a separate low-pass filter to manage this noise amplification.
So simple but noisy. Is there a better way?
A more refined option is the three-point central difference, YNT equals 12, XNT, XNT2T. This filter is an improvement because it uses points symmetrically around the point of interest if you consider the output delayed. It places zeros at both ZEO1 DC and ZEO1 at the Nyquist frequency. This means its response does go to zero at the highest frequency, F2, providing some built-in smoothing for high-frequency noise. It's less susceptible to high-frequency noise than the two-point version and often offers a better approximation of the derivative. Then there's the least squares polynomial derivative approximation. This is a more sophisticated approach related to the smoothing filters. Similar to the polynomial smoothing filter we discussed, but instead of taking the polynomial value at the center point, the slope of the fitted polynomial at the center point is taken as the derivative estimate. While it only approximates the true derivative accurately at low frequencies due to its inherent smoothing nature, which attenuates high frequencies, it provides a wonderfully smooth derivative, which is often exactly what's needed. For L2, a 5-point parabolic filter yields this derivative approximation. YNT equals 110T, 2XNT plus XNTT, XNT3T. Notice the anti-symmetry in the coefficients here, another characteristic related to derivative filters. You can even go further and create filters to approximate the second derivative by cascading two derivative stages, effectively applying the derivative operation twice. An example of this is YNT XNT 2XNT2T plus XNT4T, which can be derived from cascading two 3-point central difference stages with some scaling ignored. The second derivative is essentially the rate of change of the slope, revealing inflection points and sharp corners in the signal.
So what does this all mean for us, the listeners, in a practical, real-world sense? Why differentiate a signal? Differentiation is an absolutely crucial step in many signal analysis algorithms, particularly in biomedical applications. Think about QRS detection in ECGs, for example, where you're trying to pinpoint the exact moment of ventricular contraction. Identifying the sharpest slopes in that cardiac waveform is key to pinpointing those vital features, and these FIR derivative filters do exactly that, with the added indispensable benefit of maintaining critical timing thanks to their linear phase. Without that linear phase, you might identify a peak slope, but at the wrong moment in time, rendering the data potentially misleading or diagnostically useless.
Precisely. Finding the where and the when of signal features often relies on these derivative properties.
This raises an important question. We spent a good amount of time talking about these filters in a theoretical sense, the math, the properties. But let's bring it into sharp focus now. How are FIR filters specifically used to help us understand signals like the electrocardiogram or ECG, which is quite literally the electrical activity of your heart? This isn't just academic, it's about life-saving diagnostics and constant monitoring.
You're right. The ECG is a perfect, perhaps even quintessential example of a biomedical signal that heavily relies on digital filters, including those built on FIR principles, for accurate and reliable analysis. Its unique characteristics, very small amplitude, often contaminated by various biological noise like muscle activity, and environmental noise like power lines, make robust filtering an absolute necessity before any meaningful interpretation can occur. One critical application involves bandwidth control for different applications. The ECG signal's frequency content holds different types of information, and depending on what you're trying to learn or monitor, you need to select a very specific frequency window using filters. For a standard 12-lead clinical ECG, typically recorded in a doctor's office or hospital for detailed diagnosis, a wide bandwidth of typically 0.05 Hz to 100 Hz is required. Why so wide? Because cardiologists need to capture all the subtle morphological changes in the waveform, the tiny nuances of the P wave, the precise structure of the QRS complex, and the delicate contours of the T wave and ST segment. Missing even small, high-frequency components from muscle tremor or allowing low-frequency baseline drift from breathing to obscure things could hide crucial diagnostic markers.
Okay, so for diagnosis, you need the whole picture. Warts and all, almost.
Essentially, yes. But then for monitoring applications, such as in an intensive care unit ICU, or for ambulatory patients wearing a portable Holter monitor for 24 hours, the bandwidth is often deliberately restricted, maybe to 0.5 Hz to 50 Hz. In these environments, the primary interest is typically identifying rhythm disturbances or arrhythmias, rather than digging into minute waveform details. This restricted bandwidth effectively attenuates higher frequency noise from muscle contractions, electromyographic or EMG noise, which can look like electrical fuzz, and also lower frequency noise from electrode motion or patient breathing, baseline changes, both of which can significantly obscure the underlying cardiac rhythm, making it hard to count beats accurately or see basic rhythm patterns clearly.
So you filter out stuff that's not essential for that specific monitoring task.
Exactly. And even more specialized are filters for dedicated heart rate meters, also known as cardiotachometers, maybe in fitness trackers or simpler monitors. For reliable, quick heart rate determination, a specialized bandpass filter is often used, perhaps centered at approximately 17 Hz with a quality factor, or Q, of about 3 or 4. This filter is specifically designed to maximize the signal-to-noise ratio for detecting the QRS complex, the most prominent and consistent feature of a heartbeat, while simultaneously rejecting the lower frequency P and T waves and other noise outside that band. This allows for incredibly robust beat detection.
So this is where the filtering gets really aggressive, maybe. If this filter is so good at finding the QRS, does it mess up the rest of the signal? Does it look like a normal ECG anymore?
That's a great question, and it highlights a critical trade-off. While incredibly effective for simply counting beats, this kind of narrow bandpass filter does significantly distort the ECG's appearance. The filtered signal becomes almost unrecognizable in terms of its original shape. It would be completely unacceptable for morphological analysis by a cardiologist trying to diagnose subtle issues, but for its specific task of robustly and reliably counting beats without being distracted by other parts of the ECG or noise, it's absolutely perfect. It really illustrates how filters are designed for specific purposes.
Fascinating. Okay, so tailoring the bandwidth is one major use. What about finding the QRS complex itself? That seems like a core challenge.
It is. And let's look at a classic, groundbreaking example that integrates many of these concepts. The QRS detection algorithm, specifically the one developed by Pan and Tompkins. This is a multi-stage signal processing pipeline that extensively leverages digital filters, many of which are implemented as FIR filters or use FI principles like linear phase differentiation. The ultimate goal is to reliably identify the QRS complex, which represents the electrical depolarization of the ventricles, essentially, the main electrical event of a heartbeat. It usually involves several steps. First, a bandpass filter. This is the crucial first step in their algorithm. It's often realized by cascading a low-pass and a high-pass FIR filter, or designed as a single bandpass filter. This filter isolates the predominant energy of the QRS complex, which typically resides in a frequency range centered maybe around 10 Hz or a bit higher. Why this range? Because the QRS is a relatively rapid, high-amplitude event compared to other parts of the ECG. Simultaneously, this filter effectively attenuates the low frequencies associated with the slower P and T waves and baseline drift, as well as the higher frequencies stemming from EMG noise and power line interference. It's like using audio EQ to zero in on the specific sound of the QRS.
Okay, isolate the QRS frequencies first. Then what?
Second, differentiation. After this initial bandpass filtering, the signal undergoes differentiation. As we discussed earlier, this process highlights the steepest slopes in the signal. Since the QRS complex typically exhibits the highest and sharpest slopes in the entire ECG waveform, differentiation helps to emphasize it dramatically, making it stand out more clearly from other waves like the P wave, which might have similar amplitude but slower slopes. FIR derivative filters are ideally suited for this particular task due to their linear phase properties, which are absolutely critical here because they prevent any timing distortions of these vital slopes. A distorted slope could lead to a misidentified QRS onset or offset time.
Right, amplify the sharpness.
Third, squaring. Following differentiation is a nonlinear step, squaring the signal point by point. This transformation does two important things. First, it converts all data points to positive values, which simplifies subsequent peak detection. Second, and crucially, it further accentuates the higher frequencies characteristic of the QRS complex, which were emphasized by the differentiator, making them even more prominent and easier to detect by amplifying the large peaks from the QRS much more than smaller amplitude variations.
Make the peaks bigger and positive. Makes sense.
Fourth, a moving window integrator. The squared waveform then passes through a moving window integrator. This is essentially a smoothing operation that calculates the sum, or average, of the signal over a defined moving window of time, maybe around 150 milliseconds long, roughly the duration of a QRS complex. This provides a feature signal whose amplitude is related to the energy in the original signal over that window duration. It helps merge the multiple peaks that might arise from squaring a differentiated QRS into one broader, smoother peak, making it easier to detect reliably and less susceptible to individual noise spikes. This integration step can often be realized with FIR averaging techniques.
Smooth out the squared signal to get one nice peak per heartbeat.
Exactly. And finally, fifth, thresholding. The final stage involves applying thresholds to this integrated signal to reliably detect the peaks that correspond to the QRS complexes, ultimately identifying each heartbeat. These thresholds are often adaptive, meaning they adjust automatically based on the recent signal characteristics like peak heights and noise levels, ensuring robust detection even if ECG signal quality varies over time or between patients.
So the overall impact here is profound. Through this carefully cascaded filtering and processing approach, bandpass, differentiate, square, integrate, threshold, FIR principles play an absolutely critical role in precisely extracting the QRS complex from a signal that's brimming with noise and other biological components. This meticulous process enables not only accurate heart rate determination and rhythm analysis, but also the crucial feature extraction necessary for diagnostic purposes. It's really how we go from raw, noisy electrical activity to actionable, life-saving medical insight. It's a testament to the power of breaking a complex problem down into manageable, filtered steps.
It really is a beautiful example of signal processing in action, solving a very real and important problem.
Beyond just cleaning up unwanted noise, which is clearly vital for direct analysis, can FIR principles actually help us manage the sheer volume of medical data that modern instruments generate? Think about Holter monitors recording for days. That sounds like a different kind of challenge, entirely not just about clarity, but about efficiency and storage.
Absolutely. The smoothing capabilities, which are a hallmark of FIR filters, are directly and incredibly effectively applicable in the realm of data reduction, particularly in the post-processing of compressed signals. For example, let's consider algorithms like AZTech, amplitude zone time epoch coding, which were developed specifically to significantly reduce the storage or transmission requirements of ECG data, crucial for long-term monitoring or telemedicine applications where bandwidth might be limited. The AZ-Tech algorithm, in essence, works by decomposing raw ECG samples into sequences of plateaus, flat lines, and slopes, straight lines, approximating the entire waveform with piecewise linear segments. It only stores the endpoints and durations of these segments. While this method is highly effective at reducing the volume of data, sometimes achieving compression ratios of 10.1 or more, the reconstructed signal often exhibits what's graphically described as a jagged appearance due to its step-like quantization. Imagine trying to draw a smooth curve by only using short straight lines and flat sections. It will inevitably look blocky. In its raw reconstructed form, this output is usually deemed not clinically acceptable for a physician to interpret accurately, as it lacks the fine detail and smoothness of the original ECG.
So you've got a highly efficient compressed signal, but it looks terrible when you try to view it. That's not very helpful for a doctor trying to spot subtle abnormalities.
Yeah.
Exactly. You save space, but lose visual fidelity. This is precisely where FIR smoothing filters become absolutely crucial. After the initial data reconstruction from the compressed code, a curve smoothing algorithm or a low-pass filter, very much like the FIR polynomial smoothing filters we discussed earlier, is applied. This is done specifically to remove those jagged discontinuities and restore a more natural, clinically usable waveform appearance. For instance, if we take an L3 polynomial smoothing filter, a 7-point filter, a specific set of symmetric coefficients like 2, 3, 6, 7, 6, 3, 2 divided by the sum, which is 29, not 21 as mentioned earlier, checking the source again is key, would be used. This particular smoothing function acts as an elegant low-pass filter to reduce the sharp, artificial edges introduced by the compression and reconstruction process, essentially rounding off the corners. The impact here is significant. While any smoothing can, by its nature, introduce some minor amplitude distortion or slightly blunt sharp features, its primary benefit is transforming a highly compressed and then reconstructed signal into a much more acceptable and interpretable form for clinical review. This perfectly highlights how FIR filters are not just for initial noise removal from raw data, but also integral for enhancing the quality and clinical acceptability of data after other complex processing steps like compression. They are truly essential components in the pipeline that delivers usable, actionable information from complex, often enormous, data streams, making technologies like remote patient monitoring or vast patient databases far more practical and useful.
So they help make compressed data usable again. Another key role. We've spent a lot of time on FIR filters, and for very good reason, highlighting their rock-solid stability and that beautiful, pristine, linear phase response. But you briefly mentioned IRR filters earlier, infinite impulse response. How do they stack up against FIRs, and why would an engineer choose one over the other in different scenarios? It seems like FIRs are almost perfect for critical applications, so there must be significant trade-offs to consider, right?
That's an insightful question, and it's an incredibly important comparison because both FIR and IRR filters are powerful tools in the digital signal processing toolbox, but they truly excel in different scenarios due to their fundamental structural differences. It really comes down to what you prioritize in a given application, fidelity or efficiency, usually. To briefly define an IR filter again. Unlike FIR filters, infinite impulse response IRR filters fundamentally use feedback. This means they are recursive. Their current output depends not only on current and past input samples, but also crucially on past output samples. It's a closed-loop system. The output feeds back into the input side of the calculation. As the name suggests, if you give an IRR filter a single impulse, its response theoretically continues indefinitely or infinitely, though in practice for a stable filter, it eventually decays over time towards zero. This feedback mechanism is what gives IRR filters their distinct characteristics and, importantly, their potential computational advantages.
Feedback. Okay, that sounds like the big difference. How does that change things?
This feedback mechanism leads to several key contrasting characteristics for IIR filters when compared to FIRs. First, let's talk stability again. IR filters are not inherently stable because they use feedback, their poles, and those mathematical indicators of stability we talked about can be located anywhere in the Z-plane based on the filter design. If the designer isn't careful and any of these poles end up outside the unit circle, that critical boundary on our Z-plane map, the filter becomes unstable, leading to unbounded outputs, meaning the signal can spiral out of control exponentially. Even if poles are precisely on the unit circle, they must be simple, non-repeating, for stability. Improper design of an IIR filter can easily lead to instability, which is a significant and dangerous concern in critical applications like medical devices, where a runaway signal could have catastrophic consequences. This requires far more rigorous design and verification than for FIRs.
So stability is something you have to actively design for and worry about with IRRs, unlike FIRs where it's guaranteed.
Exactly. Second, regarding their phase response, IIR filters typically do not have linear phase characteristics. This is a critical distinction that, as we discussed, can have profound effects. It means that different frequency components of the input signal will experience different amounts of delay as they pass through the filter. This results in what we call phase distortion, which alters the shape and timing relationships within a complex waveform. As we emphasize with ECGs, this can severely distort the waveform's morphology and its critical temporal alignment. The precise timing of the P, QRS, and T waves, which is vital for accurate diagnosis, could be compromised, potentially leading to misinterpretations. This makes IR filters generally less suitable for applications where precise signal morphology and timing are paramount, like high-fidelity audio reproduction or sensitive diagnostic equipment where waveform shape is key.
Okay, so potentially unstable. And they distort the signal shape. Why use them at all then?
But here's the payoff. IR filters do have a major advantage in terms of roll-off or efficiency. This is where IR filters often truly shine and make their case. For a given filter order, meaning the number of coefficients or complexity, IR filters can achieve much sharper roll-offs, steeper transitions between the passband frequencies that are passed and the stopband frequencies that are rejected than FIR filters. This translates directly to efficiency. An IR filter can accomplish a particular frequency shaping task, like creating a very sharp cutoff frequency with significantly fewer coefficients and therefore less computational effort, fewer multiplies and adds per output sample, and less memory compared to an FIR filter that would need a much higher order, maybe hundreds of coefficients, to achieve a similarly sharp transition. It's like having a very efficient, compact engine that can provide a lot of power, sharp filtering, with less fuel computation, but perhaps with a bit more vibration, phase distortion, and a small risk of breaking down instability.
So to play devil's advocate for a moment, if FIR filters offer such perfect stability in linear phase, why would an engineer ever choose an IR filter? Where would that efficiency advantage actually tip the scales?
That's the crux of the design decision. Despite the IRR filter's potential for sharper roll-offs with fewer coefficients, the FIR filter's guaranteed stability and perfectly linear phase are often the decisive factors when signal fidelity is paramount. For applications like our ECG analysis, where preserving the exact timing and the precise shape of the P, QRS, and T waves is absolutely crucial for an accurate diagnosis, the linear phase of FIR filters is invaluable, even if it might mean a slightly higher computational cost or a slightly less sharp filter for the same cost. When absolute predictability, unwavering stability, and waveform integrity are paramount, FIR filters are generally the preferred choice, offering a level of confidence that IR filters, with their feedback loops, simply cannot provide without very careful and often complex design considerations to ensure stability and perhaps even attempt phase correction afterwards. However, where efficiency truly matters most, IR filters shine. Think about resource-constrained devices. Tiny IoT sensors running on batteries, low-power embedded systems in portable gadgets, or certain consumer electronics where every millijoule of power and every byte of memory counts. In these cases, if some phase distortion is acceptable, for instance in certain audio effects where a creative distortion might even be desired, or in some control systems where only the signal's magnitude matters, or in data compression where the ultimate visual waveform isn't the primary goal, then an IIR filter's ability to achieve a steep filter with far fewer coefficients means lower power consumption, smaller memory footprint, and faster processing with simpler hardware. So it's a careful balancing act. Integrity versus efficiency.
Got it. So FIR for fidelity and safety, IRR for efficiency when some compromise is okay?
That's a good summary. And the source material, Tompkins, also briefly touches on integer filters in another chapter. These are mentioned as a special class of recursive filters designed entirely with integer coefficients, no fractions or decimals. While primarily recursive and thus sharing some characteristics with IIR filters in terms of feedback, their integer-only design allows them to operate at significantly higher speeds than traditional floating-point designs, especially when used with slower microprocessors or specialized fixed-point hardware. They are particularly useful when very high sampling rates are required, but computational resources are limited. Their design concepts, like placing zeros on the unit circle to attenuate specific frequencies, a technique also used in designing FIR notch filters, demonstrate how different filter types, despite their fundamental differences, recursive versus non-recursive, integer versus floating point, often share underlying mathematical principles in the continuous innovation of filter design to optimize for various constraints. It's about finding the right mathematical structure and implementation for the problem at hand.
Always more to learn, always new ways to optimize. Hashtag outro. Wow, what an incredible journey into the subtle yet profoundly impactful world of FIR filters. We started by contrasting the foundational shift from the messy, continuous world of analog filtering to the precise numerical domain of digital filtering, truly appreciating why that transition was so revolutionary. Then, we really unpacked the essential, almost deceptively simple building blocks: storage, delay, multiplication by a constant, and addition, realizing how these three basic operations form the bedrock of all digital signal processing.
From there, we dove deep into the unique advantages that set FIR filters apart. Their inherent guaranteed stability that ensures predictable operation, their precise linear phase response that perfectly preserves signal timing and shape, and their relative ease of design compared to their recursive cousins. We saw how these filters are ingeniously realized through different computational methods like direct convolution for simpler filters and the much faster fast convolution using FFTs for more complex ones, optimizing for speed and efficiency depending on the scale of the task. We also explored specific types, such as the gentle touch of polynomial smoothing filters for noise reduction, the surgical precision of notch filters for zeroing out specific unwanted frequencies like power line hum, and the diagnostic power of derivative algorithms used to precisely highlight vital changes and slopes within a signal.
And we really brought it home by understanding their absolutely vital role in biomedical signal processing, particularly in cleaning up and analyzing complex ECGs. From ensuring accurate QRS detection, literally identifying heartbeats with unwavering confidence using that multi-stage process, to refining reconstructed data for clinical acceptability after compression, FIR filters are working tirelessly, often invisibly, to turn raw data into life-saving information. We even briefly touched on their cousins, the IIR filters, to highlight why FIR often wins the day when signal integrity and predictable behavior are paramount, despite IIR's potential efficiency gains.
The profound ability of FIR filters to maintain signal fidelity without distorting crucial timing relationships is truly invaluable in so many fields. It ensures that the processed data accurately and reliably reflects the underlying biological phenomena, or the original audio signal, or whatever is being measured, directly contributing to better diagnoses, safer patient care, higher fidelity sound, and a deeper understanding of complex systems. It's really an example of elegant mathematics solving complex, real-world problems.
So the next time you hear about a digital filter cleaning up a signal, whether it's making your favorite music sound clear, or allowing your phone to filter out background noise so your voice comes through during a call, or, more critically, helping a medical device precisely monitor vital signs and diagnose conditions, remember the invisible, unwavering precision of FIR filters at work. It's truly everywhere, a silent guardian of data integrity. And this leaves us with a provocative thought, maybe something for you to ponder. What other everyday signals might benefit from a filter that ensures perfect timing and absolutely no phase distortion, perhaps even in areas we haven't considered yet, like, say, the sensor fusion in autonomous vehicles, or the feedback loops in advanced robotics, or even rendering hyper-realistic virtual reality environments? And how might continuing advances in VLSI, that's very large-scale integration, the technology that packs millions, now billions, of transistors onto tiny chips, make even more complex, computationally intensive, real-time FIR filtering possible in tiny portable devices? Could this further revolutionize personalized medicine and potentially take advanced medical diagnostics right into your home, always delivering perfectly undistorted, reliable data?
Lots to think about. Keep exploring, keep learning.
We'll catch you next time for another deep dive.